In the last 10 years, the real cost of microelectronic circuits has halved every year. Computer power is now so cheap that even the smallest company can feel the effects on productivity and on the workforce. At this wood yard in a small village in Lancashire, they make roof trusses. The wood has to be guaranteed in strength to a strict British standard, and they can only use pieces stamped with a kite mark before assembly. Peter McLaughlin is a trained wood grader with a license to use his own personal stamp to put the kite mark on wood he judges to be good enough for the job. Wood grading is a question of experience and of rule of thumb. For example, the grain mustn't deviate more than a certain amount. Clusters of knots might make for an unacceptable weakness, and to find out he needs to plot the likely way they run through the wood. This all takes time. If Peter is uncertain, he tends to err on the safe side, downgrading the wood and therefore reducing its value to the yard. But this yard is now relying less and less on human assessment, less and less on Peter's judgment. Because this is a wood grading machine controlled by the inevitable microcomputer, operated by two relatively unskilled men. Unlike Peter, it measures the actual strength of the wood by stressing it one way and then the other, doing an instant calculation and failing or passing it in a tenth of the time Peter would take. Besides printing on the kite mark, it sprays on coloured ink to show where any weak points are. Without the machine, the yard would probably employ 2 more visual graders or import graded wood. Wood for the trusses has not only to be strong, but cut accurately to the right angle and the right length. If 2 different customers order different sizes and shapes, all the angles and all the lengths would be different. In the office, Paul Kavanagh used to calculate all the dimensions himself before passing them on to the yard. Now, a few £100 worth of microcomputer does the job more quickly and far more accurately than he ever could. So you see, the computer can help not just in the processing of numbers and information, but, and this is just as important, controlling things in a much better way than before. The wood grading machine, for example, was doing over 100 calculations a second as that wood went through, checking that the strength is within defined limits. And that story highlights some of the things we shall be looking at in this series. How small companies as well as large can benefit from the micro. How it affects jobs, especially semi-skilled and clerical jobs, the wood grading and the calculating, for example. How access to more accurate, more immediate information forces management to be more professional. How rapid change is forcing a rethink about consultation and working practices and training. In short, managing the micro is about managing change. Now, some say that now microelectronics is so cheap, it's a revolutionary technology. Well, is it? What's so special about it? What's different in kind between the new technology and the old? We can think of traditional technology like this. What goes on is completely predictable, and it is determined by the ironmongery. If we want to alter things, we have to alter things physically by putting in more hardware. With new microtechnology, it's not immediately obvious what will happen, because what does happen depends on a program of instructions fed in from the outside. The crucial difference is that the instructions, the software, can be changed to make the ironmongery, the hardware, do different things without the need to alter the hardware physically at all. So it's this flexibility, this software control, which is the key to the new technology. And the tools of the new breed of engineer, the software engineer as he's now being called, are not the screwdriver, the spanner, or even the soldering iron, but the pad of paper and the keyboard. Now, here are 2 chips, and each one is a complete computer. They started out identically. This one has had the memory program to control and time a washing machine, and this one a microwave oven. But this one could equally well control a model train set or a toy car. It would need to have been given different instructions. But the computer on a chip is no use on its own. You have to be able to get information into it, say in the form of electrical signals from a keyboard or a temperature sensor, as in a washing machine, or it could be a microphone or just a switch. And you have to be able to get information out of it if you want to do anything useful, like giving you information on a screen, or turning on a hot water tap, or switching on a motor, or controlling a heater. So, any computer system consists of these input sensors and output devices linked to a central processor and governed by instructions in the form of a program held in its memory. So let me see if I can demonstrate how one works. Now, here is a toy conveyor which is being controlled by a proper microcomputer. Now, what's happening on the conveyor is the number of items are travelling along. They're all different colours, and as they travel along, they're sorted by colour. Blue ones in one hopper, green in another, yellow in another. How is it done by a microcomputer control system? Right. An item comes along and a sensor looks at it and detects at once from the intensity of the light that it gives off what colour it is. So it sends a little message along to the computer saying, I've just seen a yellow one. It travels along to the next sensor. The sensor says, yes, it's arrived here. So along until it reaches the entry to the hopper, which is its destination. At which point, the message comes from the computer to the activator, pushing the piston, and it gives it a shove, bang, and it goes into the hopper. And it is as simple as that. Input and output. The message comes along. Here it is. It's ready now. Out goes the message. Right. Give it a shove. Now, it's infallible, it's completely self-contained, it can work, so why do we need the software engineer? Well, we've got one, Jeff Vincent, and it's your baby. Why do we need you?
Well, first of all, to write the program in the first place.
And the program is lodged in here?
That's right, it's stored in the memory.
So all the instructions, everything that happens, you, as it were, composed?
Yes.
And how long did that take?
A program like this, about 3 weeks.
And having done it, are you then satisfied with it, or can you change it just in a flash?
Well, yes, this one I've got in memory so that I can change it. So I can sit here at the terminal and make it do something different.
I mean, put the blues in a different one?
That's right, yes, I've got the line here displayed on the terminal that makes blues go in the first hopper and greens go in the second hopper. Now I can change it. If I just enter something different...
I won't even ask what that message is that you're sending. Only the computer can understand that.
That's right. Now I can make the yellows go in the first hopper.
Yes. I'd better put some in for you to do this. Tell me when.
And the blues in the second hopper.
Right.
If you can just load those up.
OK. Blues, yellow, yellow, blue. Right.
Now I can just set it going again. And this time it will run with the new information.
And meanwhile, of course, you're getting information back telling you how many have been sorted.
That's right. So I've got an analysis here of the last run we did, which says how many yellow items there were, how many blue items, how many green items.
And if you decided that was the definitive program and you never wanted to change it again, can you then fix it forever?
Yes, what I can do is, instead of having modifiable memory in my microcomputer, I can put the program into these little devices here, which are called EPROMs. Now the program is then fixed, so it will stay there and it can't get altered, it will just run.
And you could sell that to somebody else, to anybody else who had this kind of machine
yes, that's
in the
right.
factory. And would this program, in fact, operate a full-size machine, not just a toy?
Yes, certainly. It doesn't need to be this size at all.
Excellent. Well, thank you very much. Well, you see, small computers are being used to control an increasingly wide variety of industrial processes, all from fish farming to brewing to steel making. We've been interested to see how they're helping industries which have been suffering badly in the recession to compete. So we went to look at two companies in the northwest of England. New Waterside Paper Mill near Blackburn. Here they use scrap to make the paper for all those buff envelopes loved by bureaucrats up and down the country. The paper is made on two elderly machines. Until recently, trying to keep the quality of the paper high and the cost low has meant the constant attention of men working in very noisy conditions. But recently they have, as it were, bolted on and tailored an all-purpose British computer control system. Besides juggling with all the variables which the men used to control by hand, it also gives a graphic display of the whole plant. But how did they react?
Well, we didn't have a lot of confidence at the start. It took a few months to get the personnel really to find out that they had confidence in it, that it would actually work.
And what's it meant to you personally?
Well, personally, it's meant tighter control over the paper. I think the customer can be more confident that the paper he's getting is within the specification. And I think I can rest easier now when I'm not here.
The sensors and the control devices cost more than the computer itself. One of the more obvious is this one, which moves continuously over the paper, sending through beams of radioactive particles and infrared light to detect the water content and the density. In the old days, samples had to be taken off and analysed by hand. The computer gives minute-by-minute control of the pulp feeds, and most important of all, of the supply of energy which heats the drums which dry the paper. It's here that some of the biggest savings are being made. But what savings? And how long has it taken to get it right? Well, getting the software program right was the responsibility of the computer manufacturer in collaboration with the staff at the mill, and they're still modifying and improving it. But the basic work took 13 months, and now, of course, other mills can benefit from the work. Productivity has increased from between 10 to 15%, and the shop floor has gained through better working conditions and a productivity bonus scheme. And the system has paid for itself in just 18 months, which is about average for this kind of application. But now some homegrown microelectronics. This, not to put too fine a point upon it, is a knicker factory at Macclesfield in Cheshire, and Macclesfield is traditionally a silk manufacturing town. The garment-making industry, and indeed the textile industry as a whole in Britain, is having a bad time because of foreign competition. A flood of cheap imports from the Pacific, from Korea and Taiwan and Hong Kong, is putting a lot of British firms out of business. But this firm is prospering and can compete. Sandra here is sewing the lace on the bottom of petticoats, and she used to do it as a piece of continuous machining. So she got a string of petticoats joined together like this by the lace, and then she had to snip off the lace and fold the garments. And that was both a waste of material and a waste of time. But she doesn't do it like that anymore, because clamped to her machine is this little black box, this brain, which controls the whole operation. Now, without being too technical, let me try and explain what happens. Sandra feeds the material into the machine, and there's a sensor there which detects that the material is there, and only then can she start the machine. Right, so the piece goes through, and when it's passed through, the sensor then detects there's no material there and stops the machine. There's a little counter which counts the remaining stitches along the lace, cuts the lace, and at that point you'd expect the whole piece to fall onto the floor. But it doesn't, because the activator at the back there traps it, and there's also a vacuum suction to hold the piece there. And then, when the next piece goes through, off comes that one, folded onto the conveyor, and the job's finished. Now, if you think that that doesn't add up to very much, let me explain that this machine has increased productivity by 111%. And also, I think, a happy operator. Which do you prefer, the old method or the new one?
I prefer the new method.
Why?
You make more money on it.
We have a long tradition of development here, and we set it to the workforce by doing it completely professionally. The job's got to be right, it can't be Heath Robinson, it's got to look professional, and that's the way we've done it.
In other words, they believe that if you're going about it the right way, then there's something in it for them too.
Absolutely, and we have proved this. Their wages have gone up, the customers' prices have come down, and we've tried to make a little more profit ourselves.
So in a sense, it's attitude much more than technology that determines success.
Yes, it needs the absolute dedication of top management to push it through, force through the difficulties before you can make these things work. It's not just a bit of equipment, it is someone who's dedicated to its success.
People like Wilf Hyde, the development engineer, who taught himself about micros, helped by a course at the local technical college, and who designed the Halle black box.
Take it out again. OK, try that, please.
Now he's working on a new version to do away with the trivial task of snipping off the remaining quarter of an inch of thread on these petticoats. The company believes that its policy of continuous innovation is what keeps it ahead. But isn't there a danger of being carried away?
Obviously, the technology is advancing at a much greater rate than we can use it. We want to be very careful, though, that we don't overcomplicate and get dazzled by what can be done with a microchip. We have to stay practical, and we've got a lot of developments on the drawing board at the moment.
So, assuming that you don't go mad about the new technology, you would say it is nothing to be afraid of?
Absolutely not. It's just a tool, just as many other things are. It's just a tool which we're using, and there's nothing to be afraid of. It's quite straightforward and simple.
But an essential tool for staying in business?
Yes, absolutely.
Unfortunately, that kind of awareness is far from universal. Meetings like this one, held to introduce groups of managers to the government's microelectronics applications program, have shown where some of the problems still lie.
The companies have achieved a payback in between 1 and 3 years.
I'm not sceptical. I think what you say is completely right, and I can see from what you say that the applications that we could put it to in our own company.
Yeah.
But the point is, you've got, I mean, I'm only middle management. You've got to sell this to senior management, and most of our senior management are men in their late 50s and early 60s, and I believe that you would have a difficulty selling it to them, quite honestly.
And yet, in theory, a microcomputer could be used to control any situation which can be precisely defined, provided you can get useful information about that situation into and out of the micro. The recession apart, plenty of companies have gone out of business because they were unable to match or were not aware soon enough of the technology that was creeping up behind them, being used by their competitors. Some got into the micro game, but too late. Some rushed in too quickly and got their fingers burned. Things are changing so rapidly that a company's system of keeping up to date may not be adequate, and just reading the trade press might not be enough. A development in one field might affect you in another. In one company that we know of, they've given a researcher the job of distributing a selection of cuttings from a whole range of scientific and technical journals to management every month, in the hope that this lot will help to keep them in touch with technological change. And they've also set aside a room full of microcomputers to encourage any of the staff to get experience of using them and to see if they could suggest ways of using them in their own departments. I want to show you one way of using them which tickles me greatly. And this is the application of a microcomputer to a lighting system, say in your own house. Now, there's a ring main carrying the normal mains voltage which is connected to all the lights in the house. But the switches have wires leading to them which carry only 5 volts. This means they can be very thin wires, that you can touch them without getting a shock. And of course, I suppose you can hide them behind the wallpaper. And then, when you press a button, beep, the light goes on. Now, how does that happen? Well, what happens is this. When you actually press your little button, a signal goes to the microcomputer and says, please, can we have the light on? And the signal goes from the computer to the light saying, kindly switch yourself on. All happens just like that. Click. Off, on, off. You have a switch at both ends of the house, obviously simple things like that. But you can do all sorts of things with this. You can have the kind of light where you, it begins to dim steadily to give you a signal that it's going to go out soon because it's perhaps a staircase that's left open. It could have the kind of thing that you need where you have deaf people in the house, where you need a light that is an alarm because they can't hear anything. And in fact, I'm told that, you know, the world's running out of tungsten, and in 30 years they'll say there'll be none. One of the great virtues of this is because the light comes on from nil voltage, that in fact the life of the bulbs will be much longer. Now, of course, this is yet to be accepted by the electricity industry, but just think that if this does prove to be practicable, think of the number of people it could affect. The makers of switches, the makers of conductors, of wire, could affect the building industry, architects, designers and their trainees. You see, even if you are aware, if you do see an opportunity, you're going to need advice, good advice. But what can a small company expect in the way of help if it has a problem which could be solved by the application of microelectronics? Take, for example, this engineering works in North London, which employs only a handful of people. One of the components they make here, they make in large quantities on a machine which is designed to work unattended, and that's where the problem lies.
The machine was designed to produce this component, which is a rod which had a thread and a chamfer at each end. Previously, it had been made by conventional means on casting lathes, doing operations on each end and then reversing it and doing the other end. This obviously was very time-consuming, and this machine was designed to enable the whole sequence of operations to be carried out in one without rehandling the component. The problem now is that, having got the machine working satisfactorily, we are faced with a situation where the components are coming off the machine at quite a high rate, and they have to be manually checked to ensure that they are not going out of tolerance. If they do go out of tolerance and the fact isn't noticed, then obviously we can produce a lot of very expensive scrap very quickly. So we would very much like to have some automatic method of gauging the components, which would enable us to put an automatic stop on the machine if they did go out of tolerance.
And this is Mike Wilson's component, the rod with the thread on the top. And what he wants to have is something which will control that so he knows exactly if they're getting it wrong. And the questions we want to ask is, would a microprocessor help in that? And could the government help? Because I have with me Jan Stewart of the Department of Industry, MAP. Now that's what? Microelectronics?
That's right, Brian. It's the Microelectronics Application Project.
Now, what do you think microelectronics might possibly do for Mike Wilson with his widget?
Well, Mike Wilson's problem comes in 2 parts. Firstly, he's got to find a way of measuring this screw thread that he's producing. And he's got to find a way of doing that cheaply in a way in which he can determine when it goes out of tolerance.
Ideally constantly, so that no one gets through that's wrong.
Well, that's right, because it would be nice for him to be able to check every single one of them, which is something he can't even do with his own human operatives.
Now, could he do it in any kind of optical way?
Yes, there's a number of different techniques that could be used. There's an optical technique, and certainly throwing a silhouette of the thread against a background. As you can see from this silhouette, it produces a nice black image, which could be measured optically. But there are problems with that.
Well, what about do you think microelectronics could do it more simply?
Microelectronics may help once you've got the basic measurement made, but which basic measurement you choose will set the scene for how the microelectronics can solve the problem of making those measurements.
I mean, would it be worth him getting some consultant in to have a look and see whether it's feasible to apply microelectronics to that?
Well, that's exactly where I think he can get some help. A consultant who is a specialist in microelectronics and an applier of microelectronics can look at a number of different techniques for measurement and assess quite rapidly how microelectronics could assist in this particular case.
And under your scheme, I mean, under MAP, would the government help to fund this?
Yes. Where Mike Wilson is looking for using a new technique, in this case in a production process, though also in the case of making products, then part of the scheme that you mentioned, MAP, which is one of many government schemes, will help, for example, to provide something towards the cost of employing a consultant.
And how much is something?
Well, in the case of the MAP scheme, what is offered is the total cost of employing that consultant up to a limit of about £2,000.
Now, is £2,000 enough? I mean, is that just a very small part of what it's going to cost him to have a feasibility study, or will it virtually pay for it?
It'll pay for an initial feasibility study, not for the whole thing.
But would it pay for us enough to persuade him whether it was worth going on or not?
Well, that's what it will do, because £2,000 will pay, even the £2,000 limit is enough to pay a consultant to spend 10, 15 days looking at Mike Wilson's problem and reporting at the end of it in some detail on the way in which he could go about it and the advantages and disadvantages and the likely costs.
Now, have lots of people taken up this offer from the government?
Yes, there's been a very good response to the scheme. We've had over 2,000 clients applying who have got grants through the scheme for feasibility studies.
I mean, you're still open to offers, are you?
Oh yes, and they're coming in at the rate of about 95 a month. But nevertheless, that's still a very small number compared with the large number of companies like Mike Wilson's in the country.
So you're looking for more?
Certainly.
I mean, and is it a boring business to apply, endless sort of waiting and filling in forms, or do you act quickly?
No, we're applying new technology through the scheme, and we expect the scheme to work in a new and crisp way, and it does, because the procedure for applying for a grant is straightforward. It takes no more than a few weeks to get a decision as to whether to go ahead or not and whether to use that consultant. But they've got to come to us first.
And I mean, I take it the whole thinking behind this scheme is that the chances are that the microprocessor will prove to be useful and will be developed and applied.
Well, that's our firm belief, and it seems likely from what we've seen that microprocessors can be applied in 3/4 or more of the cases like Mike Wilson's of machinery, sequencing systems and so on.
Good, well that we will have a look at in another programme, because next week we shall in fact be looking at what is involved in getting a micro into a new product. In the meantime, if you are interested in details of the government's MAP scheme, if you drop us a line, we'll pass your letter on to the Department of Industry. So till then, goodbye.